Welcome back to the horizon. You're locked into the frequency of the future, where we separate the high signal breakthroughs from the low frequency hype. I'm your host. Let's check the manifest.
Today we are doing a deep dive into some really fascinating technical reports. They show a fundamental shift happening in space operations.
A shift away from remote control.
Exactly. We're charting the migration from a human, with a joystick, so to speak, to full, coordinated, autonomous machine intelligence.
Right. Our mission today is to really trace that transformation. It's a journey from, those robust deterministic algorithms,
The old if-then rules.
the classic human-written if-then rules, to this new era of systems that are learned, flexible, and decentralized. And this isn't just about making things a little more efficient.
No, it's essential.
It's absolutely essential for managing these huge satellite constellations, and more than that, for enabling deep space missions where Earth-based control is just. It's impossible because of the time lag.
And our sources really map out this entire progression. We start small with AI optimizing a single satellite's maneuvers, then we zoom out to coordinating hundreds of them at once.
And then we look forward.
And then we look to the really revolutionary stuff. Self-healing, robotic swarms, autonomous construction on other planets. We're drawing heavily from documents like the NASA Autonomous Systems and Robotics Roadmap, or ASR.
Okay, let's unpack that. Let's start at square one. The single agent challenge. If you're a satellite operator, efficiency is everything. Fuel is money.
And every single maneuver, every delta V, it counts.
So we looked at research that focused on one of the most basic tasks. Get a satellite from a messy, non-ideal starting orbit into a very precise, polar, circular one.
And the difficulties and the constraints.
Yeah.
The researchers, they limited the satellite to only 30 tiny impulse changes. Just 30.
That's not a lot to work with.
Not at all. And they're constrained to just the 6 basic directions: forward, back, left, right, up, down. The number of possible combinations for that 30-step sequence is walls math.
So traditional methods just hit a wall.
They do. An approach where a human tries to program the perfect path, you just can't search that entire solution space. It's too big.
And this is where that biological inspiration comes into play. They didn't program the answer.
They let the answer evolve.
Right.
Exactly. They turn to evolutionary algorithms, specifically something called a genetic algorithm, or GA.
And how does that work in simple terms?
Think of it like this. That 30 impulse sequence is treated like a chromosome, a string of genes. They start with a whole population of just random impulse strings.
So a bunch of random guesses.
Bunch of random guesses. And then the process starts. Mating, crossover, mutation. It's literally survival of the fittest, but for computer code.
The fittest sequences, the ones that get the satellite closest to the goal. They get to breed and create the next generation.
Precisely. The new children sequences take parts from both parents, that's the crossover, and you introduce tiny random changes, which is the mutation. Over thousands of generations, this process just naturally pushes the population toward the best possible solution.
So how did they define fittest here? What was the scorecard for a good maneuver?
The fitness score was crucial, and it had 2 parts. First, they wanted the orbit to be perfectly circular, which means it has an eccentricity of 0.
Okay.
And second, they wanted it to be polar, so an inclination of exactly 90 degrees.
So the algorithm's entire job was to get those 2 numbers as close to 0 as possible.
Yes. The score was the distance from 90 degrees, plus the eccentricity. The lower the score, the better. If the algorithm found a sequence that gave you a score near 0, they knew it had found an incredibly efficient path.
And the results?
Decisive. The GA successfully planned the sequence and got fitness scores of less than 0.1 across all 4 test orbits.
Wow. So that's highly polar and highly circular? A solution that, as you said, would have taken humans months, maybe?
Months, if they could find it at all. But here's the real insight for you, the listener. This is why machine learning is such a sea change. It's about generalization.
What do you mean by that?
A traditional, human-written algorithm is brittle. If you suddenly change the satellite's mass or its engine thrust just a tiny bit, that human-written code might completely fail.
Because the programmer didn't anticipate that specific problem.
Exactly. You have to code for every single contingency. The GA, though, it learned the principles of orbital mechanics inside the simulation.
So it could adapt.
To prove it, they just updated the fitness function. They stopped asking for a polar orbit and instead told it to achieve a specific size of orbit, a specific semi-major axis.
And it just figured it out.
Converged just as effectively. The algorithm generalized its knowledge of physics to meet a totally different goal. No new code from an engineer. That flexibility is the high signal, and it's vital when we go from one satellite to a whole network.
That adaptability is the key. Because now we're making that jump to managing massive constellations. We're talking hundreds of spacecraft. Think Planet Lab's Dove fleet or Spire.
And they have to coordinate thousands of observation requests every single day.
The scale is just crippling for any kind of centralized control.
Oh, absolutely. Imagine one mission control center trying to micromanage every satellite. That system is immediately vulnerable to a single point failure.
If the central brain goes down, the whole fleet is dead in the water.
And the communication burden. You're constantly sending out instructions, getting status updates from every single satellite. It's a fire hose of data.
Which is why the industry is moving to these decentralized multi-agent systems.
Right, where each satellite has some autonomy. But even then, the scheduling is a nightmare. Mathematically, it's framed as a distributed constraint optimization problem, or DCK.
That sounds complicated.
It's the ultimate coordination puzzle. In theory, you want to find the one single global schedule that gets the most observations done while using the least amount of fuel for every satellite all at the same time.
And why can't a supercomputer just solve that?
Because the complexity is exponential. For hundreds of agents and thousands of requests, the time it would take scales insanely fast. We're talking about a complexity of O of 2 to the power of agents times requests.
In human terms.
In human terms, calculating the perfect optimal solution would take longer than the age of the universe. It's just not feasible.
Okay, so that's where the smart shortcut comes in. The JPL researchers decided instead of solving the whole thing perfectly, let's break it down.
Yes. Their approach is called geometric neighborhood decomposition, or GND.
The name is a bit dense, but the idea is actually brilliant.
It is. They just exploit the orbital geometry.
Mhm.
Satellites that are in the same orbital plane flying together, they naturally see the same things on the ground. They form a neighborhood.
So instead of every satellite talking to every other satellite, they just talk to the ones in their orbital plane.
Exactly. GND breaks up that massive global problem into these small, manageable sub-problems. It delegates requests to a neighborhood. Then they use another trick, intra-neighborhood delegation, which uses an agent's position in its orbit to decide who does what. They coordinate without a ton of communication.
A distributed divide and conquer strategy. And what algorithm actually runs on this?
That's the Neighborhood Stochastic Search Algorithm, or NSS. It takes those small, well-defined subproblems and solves them statistically. And the key result here was the performance.
Better than other methods.
Superior scheduling quality? Yes. But the real showstopper was the communication savings.
The bandwidth. Tell me about the bandwidth.
NSS decomposition required an order of magnitude less messaging volume than the competing methods. That is huge. It proves that if you partition the problem smartly, you can get a high-quality global solution without flooding the network.
You get all the benefits of decentralization, the resilience, the adaptability without the constant chatter.
And that reduction in chatter is absolutely critical because when we go from low Earth orbit to deep space, communication doesn't just get slow.
It gets delayed by minutes or hours. Autonomy stops being a nice-to-have and becomes a non-negotiable requirement.
And that's the strategic driver for NASA's focus on swarm intelligence. A swarm gives you resilience. One agent fails, the mission goes on, and it enables what they call opportunistic science.
Meaning it can react to things on its own.
Yes. If a deep space sensor spots a gamma ray burst, the swarm needs to react instantly, long before a signal could ever reach Earth and get a command back.
And we're seeing tests for this right now. This isn't just a roadmap. The Starling mission, launched in July 2023, is doing this.
That's right. It's 4 small CubeSats operating autonomously, holding formation about 40 miles apart, all without real-time commands from the ground. They're testing the absolute foundations of this technology.
What are the key software components being tested there?
There are 3 main pieces. First, you have Romeo, which handles a complex maneuvering. Second is the MANET system for communications. It's a self-healing, self-patching network to keep the swarm connected.
And the third one, Star Fox. That just sounds clever.
It is. Star trackers are standard equipment used to look at stars for orientation. Star Fox repurposes those same trackers to look at the other satellites in the swarm.
So the swarm itself becomes a set of navigation beacons.
Precisely. It lets them hold their formation with incredible accuracy.
And Starling is taking this a step further. They're collaborating with SpaceX for a real-world collision avoidance test.
This is a huge immediate need. The Starlink satellites will autonomously practice collision avoidance maneuvers with the very dense Starlink constellation. This is defining the rules of the road for autonomous systems in real time in a crowded orbit. It's machines negotiating space traffic management with other machines.
Now, if we look out, say, 20 or 30 years, the vision gets even more ambitious. The Autonomous Nanotechnology Swarm, ANTS.
It is a completely visionary architecture, inspired directly by social insects. The model mission is something called TAM, the Prospecting Asteroid Mission. Imagine launching a 1,000 pico-class spacecraft,
1,000. How big is a Pico-class craft?
about 1 kilogram, powered by solar sails.
And these 1,000 tiny spacecraft work together like an ant colony.
Exactly like one. There's a division of labor. You have rulers for command, messengers for communication relays, and then specialized workers carrying different scientific instruments. The strength is in the numbers and the redundancy.
The outline mentions self-healing. That implies these. These agents are making life or death decisions for the group.
That is the most profound part of swarm intelligence. Self-healing means the swarm has to recover from damage on its own with minimum downtime. So imagine a worker unit gets hit by a micrometeoroid, its solar sail is damaged.
On a normal mission, that's a lost asset, a lost instrument.
But in the ANTS model, that faulty unit has to decide its new purpose. If the damage is too severe, it might perform a self-sacrificial act. The main scenario they discuss is a damaged worker transforming itself into a standby shield.
A physical shield
Yeah.
to take an impact.
Yes. If there's a risk, say a tiny asteroid fragment threatening a newly deployed, healthy replacement worker, the failed unit, the shield, could autonomously move into its path and take the hit.
It's a cold calculation.
It's a calculation. One expendable asset saves a mission-critical one, minimizing the recovery time for the entire mission.
That requires total delegation of trust to the machine intelligence. We've moved from preserving one expensive satellite to optimizing the survival of the collective. It's a huge paradigm shift. Let's bring this autonomy back down to a planetary surface, say, the moon.
Yes, this is also fundamental for colonization. The NASA AOSR roadmap is all about creating the technology to grow a real space economy. And that means using cooperative robotics to do the heavy lifting.
The ultimate goal is to build the infrastructure before the astronauts even get there.
That is the entire idea behind the 8-step progression for autonomous lunar site preparation. It's a construction project run by robots. Step 1, supplies arrive. Step 2, excavation starts with prototypes like RASOR, which is already at a high technology readiness level.
And then the robots are transporting materials, sintering a landing pad from the local dirt, digging trenches for power cables.
Erecting fuel depots and power systems. It's a self-building moon base. Only once all that critical infrastructure is built and tested by the robots do the humans arrive.
To make that kind of cooperation possible, all these different robots need to speak the same language. That's where Space ROS comes in, right? The robot operating system for space.
It is. It's a modified version of the open source ROS2, but they're aligning it with really stringent space software safety standards, like DO 178C.
And the vision is to create a kind of app store for it.
Yes, a registry of reusable software modules. So if one team builds a perfect mobility module for driving on the moon, another team can just download it and plug it into their robot that has a manipulation module for lifting things. It standardizes the building blocks.
Now, before we wrap up, we need to bring this all back to Earth. To contextualize why this shift to robust, decentralized intelligence is so urgent by looking at how vulnerable our current systems are, specifically in the maritime world.
The contrast is pretty stark. We're spending billions to design self-healing space swarms, but a global survey of maritime professionals show that their single most important space asset is still just GPS.
Just plain old GPS.
64% of UK respondents said it was essential. Nearly half of Saudi Arabian users said GIS input, which relies on GPS, is critical.
It's our lifeline, and we know it's incredibly vulnerable to all sorts of hybrid threats.
Exactly. We're talking about GPS spoofing, where fake signals send ships off course, or just straight-up jamming. And that's not even considering the high-end threat of an EMP, an electromagnetic pulse, from a small satellite that could cause massive network failures.
And this vulnerability drives what the users are demanding.
Yeah.
They need persistent surveillance day and night in all weather.
Right. If GPS goes down, they still need to see what's happening. That makes data from things like synthetic aperture radar, or SAR, absolutely crucial. SAR can see through clouds, see in the dark.
It's used for tracking everything from piracy to illegal fishing.
Constantly. The goal is to have decentralized surveillance that you just can't hide from.
So if we look at the whole trajectory we've charted, the story is crystal clear. We started with a genetic algorithm optimizing a single orbit. We scaled up to algorithms coordinating hundreds of satellites. And now we're on the cusp of self-healing deep space swarms that are building moon bases before we even get there. The age of learned machine intelligence in space isn't coming.
It's here, it's operational.
It's an operational fact.
And if you take that fact to its logical conclusion, you realize that the only way to solve these massive coordination problems, like building a lunar base, is by distributing the intelligence, by allowing for self-organization, and even, as we saw with the ANTS model, self-sacrifice.
So, if this next generation of space assets is designed to solve problems and sacrifice themselves without any human input, what new ethical or design paradigms do we need to prepare for as we delegate that total operational trust to a collective machine intelligence?